motion planning around that simple problem with the graph of convex sets. We can take those disjunctive constraints, but we're actually going to write them differently now. We have this sort of graph structure of there's left or right around the obstacle, and we're capturing that real combinatorial complexity more natively, okay? We can still write our convex loss functions, and we now just formulate these graph search on top of the continuous search. Of course, I'll run the example. Here's the graph of convex sets version. And the number of decision variables was not preordained. That's kind of nice because it's the path length in a graph search problem. Okay, and it solves the global optimality. That's not surprising. But the important point here, gotta stop this. The important point here is I'm going to change this now to show you what's the convex relaxation. Okay, and this one is still tight. Okay, which isn't too surprising for this very simple example, but we're going to see it works even for much more complicated examples. Okay. So back to our maze. Now we're going to find a continuous path. Oh yeah, please.
Can I ask a question?
Please, yeah.
What is the definition of how to decide which convex set to choose to design the relaxed formulation?
Good. So the question is, how do I design the convex set? In the maze example, in some of the simple examples, there's a natural convex decomposition of the space, and I'm trying to use that for the beginning examples. I'll show you the harder examples. There's a more complicated story when it's the arms going through and everything like that. That's a fundamental question that I'll try to address. And this one is easy. You can just make a box for each cell. Okay, I want to go from the start to the goal, but I want to find a continuous path. Like I'm going to walk a humanoid robot through here or something like this, right? It turns out the continuous path by some metric of path length is this. And that's coming out of a convex optimization. The convex relaxation is tight in that setting. Like when I first saw that, I thought, that's not what convex optimization should do. But it connects it's just connecting the discrete graph with the continuous optimization. And by the way, the previous formulations would have been intractable for this. Just the number of binary variables was insane. So you can make problems, the convex relaxations tighter by adding exponentials of numbers of constraints. That's not what we've done here. We've added an efficient number of constraints and got good relaxations. Okay, so I knew there was a session on hardness results and everything before us. So this is not changing. It's not defeating any hardness results, of course, right? In the particular example of this Euclidean shortest path, kind of like we showed there, there's a lot known about the hardness of that problem. This formulation provides a polynomial time algorithm. It works in arbitrary dimensions, and it is often tight. Okay, we're not saying P equals NP. We're just saying that in practice, it's almost always tight. But we know counterexamples where it is not tight. A bit like what Brian was saying. Okay, and it does solve a more general class of problems than the standard Euclidean shortest path problem. It's got some nice properties. So like if I take those sets and I shrink them down to a point, then I actually get back the original formulation. So we haven't broken this known good result. We know there's instances that are NP hard. We have all simple examples in the paper of all of the corner cases, if you will. But you can do interesting things with this. So it's a pretty expressive language. So you can, for instance, put constraints in the cost that will allow our costs to be infinite. So that means you can sort of implement constraints in the cost. And so you can add dynamics into this, for instance. And one of the first things we did was we took some of our old mixed integer footstep planning and we solved them much, much faster, orders of magnitude faster, many orders of magnitude faster than our previous approaches. But let me tell you about the differential constraints for motion planning. Okay, so here's the way I'm going to transcribe the motion planning problem down into a graph of convex sets. So now the red is the obstacle, the blue are the sets we want to stay inside. That's a convex decomposition of the space. Again, a simple example here will make the more general case. There's a natural graph. make an edge in the graph for every, if the sets intersect at all, even on a line, measure zero intersection, but if they intersect at all, I'll put an edge in the graph. And I'm actually just going to put an edge both directions. I could go either way, right? This is my source, this is my target. So this gives me a trivial graph. And then I'm not going to find one point in each set. I'm going to write an entire curve that lives in the set. So the graph of convex sets actually lives in some Cartesian product of those sets up in some high dimensional space to represent the curve, okay? But pictorially, I can just say we've got a curve that is constrained to live inside each set. If we use Bézier's curves, then we can use that with linear constraints, convex constraints. Okay, and then at optimality, we'd like to have we have constraints so that if this edge between here and here is in the shortest path, then the final node in this curve has to touch the final point in this curve, and we can add derivative constraints on that, for instance, up to some derivative smoothness. And then there's one more thing is we can't preordain the smoothness or the timing of this. So we actually have another curve that lives in each one of these sets that thinks about a time rescaling that works along with it. And we solve those all jointly in a convex way. So this is the kind of, like, if you're thinking, well, could I use this? Here's the set of cost functions that we support right out of the box. So you can have a duration, a total path time. You can have a path length. You can have something about path energy. We have other terms that we can put in for smoothness. Then you can ask for it to be differentiable up to some degree. You can have your collision avoidance constraints, saying that all of my Qs are in the union of the safe sets. And unlike most of the sampling-based approaches, this is actually for all T. We're not saying like at some sample points, this is an absolute, that curve is outside the obstacles. You can add velocity constraints. Acceleration constraints, we don't have yet. They're tough. They come in a non-convex way given our time rescaling, but we'll figure those out at some point. Then you can put bounds on the total time. You can put initial and final conditions. Okay, so that's kind of the library of optimization problems we can write in this format now. And if you solve that now, solve the maze problem. This is not actually. We downloaded a bunch of mazes and then we realized mazes all have like one solution, right? So we had to knock walls out of the mazes in order to make it interesting. So there's multiple paths and multiple solutions. And if you change your objective function from minimum distance to minimum time, you get different paths out of the same graph, right? And they're solved to optimality. So just to say it, I'll repeat it a few times just to make sure I don't try to give the impression of something more than it is, right? So we have a transcription to a mixed integer convex optimization, but with a very tight convex relaxation, right? So we're not saying P equals NP, we're saying we can solve the global optimality with branch and bound, orders of magnitude than with previous work. And in fact, it got to the point where it's so good that we basically never solve branch and bound. We don't even say you need a branch and bound solver. You can just call the convex optimization solver. We've got some rounding strategies that will take an approximate thing and make it very good, and this is almost always sufficient to obtain the globally optimal solution. Okay, now that is something that is somehow an empirical statement, like that in many problem instances, it's almost always good. So let me give you an empirical evidence for that, okay? So we started making random environments for a quadrotor, and we did the planning from start to a goal, and we just started to collect statistics given this randomly generated environment. How often are we optimal from the convex relaxation? And there's actually two different plots here. So this one, the optimality gap is we're going to solve the convex optimization, and then we're going to solve the mixed integer convex optimization and see when are they the same and when are they different. And basically, almost always they're the same. You get the optimal solution. And even when you don't, in all of our examples, you get like 2% off optimal. Like you flew through the neighboring window instead of this window. So they're really, the optimality gap in practice seems to be very, very small. There's a second question, which is if you only solve the convex optimization, can you know that you're optimal just from that without solving the mixed integer, right? Because that was the thing we wanted to avoid in the first place. You just use the lower bound and the rounded solution of the convex optimization to give a bound. And you can ask what's the gap of that lower and upper bound. And that certified optimality gap, solving only convex problems, is also very good. It's not as good as the true, in practice, it performs better than it can prove it performs. Okay, but it's pretty encouraging. Okay, how do we get to convex regions? Here's the big question, right? So the way we've done it in the past is we have approximate convex segmentation algorithms, which scale, they use an iteration between quadratic programs and semi-definite programs, and they scale to high dimensions. At the time, we were doing it with raw sensor data, so we really wanted that scaling to work. And this is a general approach that we're going to extend. And so the way you should think about it is you can do a bit of sampling. You have your initial region for your quadrotor, for instance. You have some bounding volume that you care about, and you'll just start drawing samples. But instead of building some dense road map, for instance, every time I make a sample, I'll grow a big region around that sample, and I'll come up with a small number of convex regions that tries to fill the space. Okay, and then you do the planning through that. Now, in configuration space, I showed you robot arms that have complex, configuration space obstacles. In configuration space, in the previous work, we assumed the obstacles were convex. You can't assume that in configuration space. So we've now been generalizing that algorithm to configuration space. There's two generalizations of it. One with not just nonlinear optimization that's very fast, but not certified, and then another one that does sums of squares optimization to rigorously certify. And there's a presentation on that. Alex will give a presentation on that, the details of that on Friday. But in particular, it's surprisingly effective, even in these complicated configuration space. So you take the sums of squares certificates, for example, of a bimanual, two-armed thing, and you ask for a proof that these things are out of collision. It's showing the details of this will be crystal clear on Friday, but it's trying to show that this separating plane is separating these two convex bodies in task space. And the point is that they're getting very, very, very close. It's not like we're making some coarse approximations, over here, but we can't say anything when things get tight. It's actually finding, with small numbers of space of regions, pretty good coverage of the space. Okay, so let's connect this to sample-based motion planning. So, the classic PRM, I like to use the old picture from Howie et al. So you all know what a probabilistic roadmap is. So the proposal here is almost the same, but the problem, I guess, with only using points and line segments in your roadmap is that doesn't leave any room for optimization when you're done. So the proposal here is every time you add a point, just grow the region. And instead of making 10,000 points inside there, make 10. And you can actually then leave yourself room to do continuous optimization inside the set, get beautiful guarantees, actually more guarantees than you can get in a sample-based approach that's only checking at a finite number of points. And within that convex decomposition, we can solve with the branch and bound to global optimality, or almost always with the convex relaxation. Okay, so we did a bunch of comparisons of just like how does the graph of convex sets formulation compare with PRM, for instance. I think that is the natural comparison, is because we're going to spend offline computation building the regions, and we want our online computation to be fast, similar to a roadmap multi-query kind of approach. Okay, and we compared it against PRM, and PRM with shortcutting, which of course has longer solve times, but better paths that comes out. Okay. It's interesting too, that part of this work was motivated by thinking about, there's a lot of companies out there using robots to do, they're working in the same environment almost all the time, right? Whether it's scooping salads, my friends at Dexi are scooping salads all the time, and their workspace really doesn't change. Their motions change from time to time, and so the paths have to change, but the configuration space, you could totally pre-compute that, and you should, I would think. Okay, so again, statistical analysis here. So different tasks is just going from different points in the state space, in the configuration space to the other. And if you compare the trajectory length of the graph of convex sets versus the PRM versus the shortcut, we not surprisingly get shorter paths. The PRM here was actually 10,000 points, right? And the graph of convex sets took 8 sets to pick. And we used all the same points. We tried to be super fair to the PRM. Like all the same points we used to seed the regions were also in the PRM. We used RRTs to connect, gave it every possible advantage we tried to. Okay, and the shortcut does better, of course, but is not optimal.